Good morning. I am going to talk about one of my favorite numbers. I mean, I have a lot of favorite numbers, but this one is finite. It's bigger than 1 million, and I happen to have it memorized. So I figured it'd be a pretty good number to talk about. The number I want to talk about is 2 to the 255th power minus 19. So why is that number interesting? First off, it's a prime. You can check that for yourself, although I don't recommend it because it's kind of a big number. But if you have the patience, you can confirm for yourself that it doesn't have any divisors. And the cool thing about that is if we take a prime number and we wrap it around a circle, so this circle's half full or half empty, and you imagine taking numbers and putting them 0, 1, 2, 3, 4, 5, 6, 7, and keep on going all the way around the circle until you come back to 0, then you've constructed a cyclic group of prime order. Oh, there's another dog. Hello. So that's an interesting and cool thing that you can do. And you can do that with any prime number. I could have said 5, right? And you'd have 0, 1, 2, 3, 4, and well, 5 is 0 again, right? But if we do it with a very large prime, then we start to be able to do something really cool called Diffie-Hellman key exchange, which is a fundamental kind of cryptography that we do all the time on the internet. To explain how that works, I need to first explain the discrete logarithm, I think. Hopefully that's not going to be too complicated. Imagine as we're going around the circle that we pick a step size, and that size is going to be how big of a step we want to take at once, how many points we're going to take as we go around the circle. One of the cool things about a prime order group, like the one generated by 2 to the 255th power minus 19, is that no matter what step size you pick, you will eventually go all the way around the circle. You'll eventually visit every number. And because you'll visit every number, that means that you can start from any place on the circle. So now, again, if I imagine starting at some random place and ending at some random place, well, I know that I could just take one single step to get there, of one single step size. But what if I'm not allowed to pick the step size? What if the step size is smaller or larger? Well, it turns out that if you go around the circle over and over and over again, you'll eventually get to your destination. But how long does it take? How many steps do you need to take of a given size? This is a tough problem. This is called the discrete logarithm problem. And because it's so difficult, we actually use it for building cryptography. And the main way that we do that is through what's called Diffie-Hellman key exchange. The idea with key exchange is that two people, traditionally called Alice and Bob, want to exchange a secret. It doesn't really matter what the secret is, they just need to exchange it. And there's traditionally somebody in the middle, again, traditionally named Eve, who is trying to discover those secrets that Alice and Bob are trying to share. So what Alice and Bob can do is they can agree beforehand on a group. Okay, they agree beforehand on a cyclic group, and they agree beforehand on one point that they pick. Okay, and they also agree on a step size. So if you imagine that you've got a cyclic group that you've picked, and you've picked a single point, and you've picked a step size that allows you to, like, imagine walking around the circle based on that point, then what you can do is, what Alice can do. What Alice can do is she can generate a random point, okay? And she takes her random point, and she takes the step and walks the step around the circle using her random point. And after she's done that, she sends her walked point over to Bob. Bob sends her a point that's also been walked according to Bob's random number. Alice takes Bob's partially walked number and continues walking it using her private number. Okay? So if you think about this, then we took our step size and we walked it around the circle, or around the cyclic group. And the number of times that Alice walked it is Bob's number, then Alice's number. And Bob walked it, Alice's number, then Bob's number. So they both walked the step the same number of times through the cyclic group, starting from the same point. Alice and Bob have a secret that they've shared with each other. And what about Eve in the middle? Well, she only sees these partially walked steps. She doesn't actually see the private numbers that Alice and Bob have. But if you're thinking carefully about this, you might realize that Eve does have something that she can do. If you imagine that I cut the circle up into pieces, then you could imagine that going all the way around the circle, all around the cyclic group, about once, roughly once, is equal to some other unit of measurement. So for example, with radians, it's about 6.283 radians, I think, to go all the way around a circle once. That means that it's roughly 62 radians if you go around the circle 10 times. If you go around 100 times, then it's roughly 628. So you can turn your rotations around the cyclic group, I shouldn't say rotations, your revolutions, your circumnavigations, your trips all the way around. You can count those, and you can estimate kind of roughly how many steps you would need. I'm glossing over a lot of details here. This is called index calculus, and it's very tricky because you can always do it. It's always possible in any cyclic group. So any cyclic group comes with a discrete logarithm problem, which allows for us to do key exchange, but it also comes with this index calculus family of techniques that allow you to kind of improve and, in some cases, break the discrete logarithm. And if you know anything about old school public key cryptography, you might know that traditionally we've needed really, really big keys. And this is part of why. But one thing I want to point out, part of why a circle is not a very good cyclic group for this is because the circle is really smooth. And that means that if you take a step, you know where you're going to end up. I need to use a bit of a visual metaphor here, but we'll see how this goes. So if you take a look at this pastry, you'll see that the pastry has these stripes, and these stripes cut across the circle on the edge. So now, if you imagine taking a step on this pastry, so you could start here, for example, and then you could take a step, say a step of size 1, and that'll actually take you, it won't take you over here, it'll take you around the pastry, okay? And you could imagine, this pastry is kind of flat, but you could imagine that it loops around again. And so there are finite cyclic groups that still have the same kind of shape, but they're folded up differently, okay? And that's where we get back to my favorite number, 2 to the 255th power minus 19. Because, yes, it does have a regular finite cyclic group on it, just from being a prime number, but we can put more structure on it. And one of the structures we can put on it is called an elliptic curve. Unfortunately, the convenience store doesn't sell anything that looks like an elliptic curve. But an elliptic curve is a kind of geometric shape. If you know what a circle looks like, a circle's got y squared, and it's equivalent to some kind of x squared-ish, right? So you've got y squared equals some quadratic polynomial. And that gives you something that kind of looks like a parabola, right? You can imagine a parabola, right, is quadratic. But because you've got that y squared, you kind of actually end up with a circle or an ellipse shape. You get this vertical symmetry. And an elliptic curve's the same deal, sort of. It's got y squared on one side, and then it's got a cubic polynomial on the other side in x. So y squared on one side, and then you've got an x cubed and x squared and x on the other side with some coefficients. So if you imagine a cubic graph normally looks like this, right, or maybe it looks like this, then when you vertically flip that and you mirror that, then you get really cool shapes that, you know, they wiggle and wobble. And they're hard to explain, but you can go look up examples online. There's plenty on the internet. The main trick to these elliptic curves is that you can wrap them around prime numbers. You can wrap them around circles. And when you wrap them, you don't get the clean circle of numbers that are next to each other. You get these dots that are really spread out. And if you were to force them to loop, then they kind of look like this roll. They'd be bumpy around the edges, around the circle. And the reason that it's bumpy around the circle is because it's actually this really big curve. It's this infinite curve. It goes off to infinity in one direction, these elliptic curves. But they're still relatively well behaved when you wrap them around, because once they've been wrapped around a cyclic group, they kind of stay wrapped. It's hard to, again, the visual metaphor doesn't do it justice here, you know? Nonetheless, we are coming to the crux of this, which is that if you imagine doing Diffie-Hellman key exchange on an elliptic curve that's wrapped around a prime number, then the discrete logarithm problem, the elliptic curve discrete logarithm problem, is much, much more difficult than it is in other groups. And as a result, the keys can be very, very short. And this leads to another property of my favorite big number. Remember, this is a video about favorite big numbers, not about group theory. So 2 to the 255 is a number. If we wanted to generate a random number between 0 and 2 to the 255th power, we could do it by taking 255 bits of random information, and then we've got a random number in that range, right? And because 2 to the 255th power minus 19 is so close to a power of 2, we can generate random numbers that are within the range of that prime number very, very efficiently. And so this is why it's my favorite number, because Alice and Bob can each generate only a little bit of data. They have to generate about 32 bytes of random data each. And then they perform some very basic math. They exchange their partially computed numbers. They do a little bit more math, and they've exchanged a key. It's a remarkably simple and straightforward system. There are so many cute dogs out today. Anyway, that's all that I had. I hope that this was informative, and if it wasn't, then I'm sure that you can click over and find a much shorter video that doesn't use foodstuffs for demonstration purposes. Anyway, that's all I've got. Thank you very much.